All right. Well, we're 1 minute after the hour. I think that's good enough to start with the intro slides. And I'm sure some more folks will trickle in. So welcome. This is the third 4D BGC webinar. So the 4D BGC working group, we are a SCOR funded working group that is coordinating the development of four-dimensional gridded data products from BGC Argo observations. So our main goal is to facilitate discussion and coordination among different scientific communities around developing, validating, and distributing these data products. And the ultimate goal is to enhance the access and utility of BGC Argo observations through the distribution of these gridded products that can refine our understanding of ocean biogeochemistry, improve models and reanalysis products, and inform policy decisions. This is a photo of the group meeting at the Ocean Sciences meeting in New Orleans last year. So just a couple quick updates from the working group. So this is a page that is in development right now. We're working with Biogeochemical Argo to get a data products page on the BGC Argo website. So this will be an online repository of gridded data products, and we have a couple examples here. So we'll have a group of data products that you can kind of click on and explore some information about each one, including links to the DOI for the data product and the relevant publications associated with it. So this, I believe, will be going live fairly soon. We're still kind of working out the details of the page, but this will be kind of the first deliverable from this working group. We have a working group website. I invite you to scan the QR code or go here to 4dbgc.github.io. This is where we post our webinar schedule, as well as other group activities and resources from the working group. I'll also invite everyone to join our mailing list. You can find that link to this on the group's website. And also I'll point out that we are recording these webinars and posting them on YouTube. You can find them here at this link. Or just, I'm sure, Google 4DBGC YouTube. You should be able to find it. This is also linked on our website. Okay, and with that, I'm going to turn it over to our speaker today. So we have Cara Nissen from the University of Amsterdam, who is going to be speaking about synthetic float observations from an Earth system model and how those can be used to evaluate uncertainties in BGC Argo-based analyses. And yes, I will stop sharing here and I'll turn it over to Cara.
Thanks, John. Okay, now let me share the screen.
Oh, and I will mention, I think we have a chat here that if you have questions throughout Cara's presentation, feel free to put them in the chat and we will address them in a Q&A at the end.
Perfect. I assume you can see my screen well. If not, speak up, but
Yeah, looks good.
yeah, perfect. Well, thanks so much, John and Raphael and Catherine, for the invitation to talk about a recent project of mine, of ours, in more detail. I'm going to talk about a new synthetic float data set that we would argue can be used to assess uncertainties in Argo and BGC Argo-based analyses. This is the result of a whole team of scientists listed here on the slide, which I want to acknowledge. This is a US funded work funded by the Department of Energy and involves scientists who are based at CU Boulder, University of Washington, Los Alamos National Laboratory, and now me, who has just recently moved from CU Boulder to the University of Amsterdam. So I probably don't have to, well, go in too much detail about this to this audience, but of course, thanks to Argo and BGC Argo, we have unprecedented coverage of the ocean with observational data. I just pulled a map here of the density of dissolved oxygen observations. So these are the number of floats equipped with dissolved oxygen in any 6 by 6 degree grid box. And we can see, even though we have unprecedented coverage, many regions show up as red here on the map, indicating that these regions continue to be undersampled. This becomes obvious as well if we look at the yearly coverage with dissolved oxygen profiles. And what is shown here is the average of monthly observations within any 3 by 3 grid box for the year 2024. And we see a lot of these grid boxes are kind of not covered at all, or only covered for part of the year. So really, when we're going from these float observations distributed in space and time to gridded products, it's really the questions remaining, I think, is how to quantify, how to go about quantifying uncertainties related to this sampling coverage, or in more general terms, the Argo sampling protocol. Last year, we published a paper that showcasing a new tool that we think can help address, or at least get at some of these uncertainties. We termed it Light BGC Argo. The term light here is kind of a result of a name of a Lagrangian tool that already existed in the Earth system model that we do this work in, which is E3SM, the Department of Energy's Energy Exascale Earth System model. And LIGHT here stands for Lagrangian in situ global high performance particle tracking. And this is just the ability that the ocean model of E3SM already had to simulate Lagrangian particles online during model runtime. And here what we did in this work is to kind of change the behavior of these Lagrangian particles to mimic that of Argo floats. So what this looks like is a very similar sketch to the sketches that you see of how Argo floats work, with the difference here that our Argo floats sample the modeled ocean. And it's important to note, as I said already, that these floats sample the model world online during model runtime. They thus provide the same snapshot view of the modeled ocean as Argo floats provide of the real world ocean. Our floats sample the full water column, so surface to seafloor, and as such, they are not only core and BGC Argo equivalents, but also can address uncertainties regarding to deep Argo. An important difference to real-world floats is that for just numerical reasons, it just was easier to implement. Our floats do sample the water column instantaneously. That means they're not actually displaced laterally during ascent or descent, but they record water column properties in an instant when we tell them to. In contrast to real-world floats, of course, these synthetic floats, we don't have to worry about sensors being damaged when sea ice is present at the ocean surface. So our floats can be localized at all times, and they sample the whole water column at all times, whether there's sea ice present or not. And with this system, we then can, as a user, can then define the set of variables to be sampled on these floats. So again, in contrast to real-world floats, in this perfect model world, we're not restricted by the sensors that we have available, but can in fact sample any diagnostic or prognostic model tracer that we would like to record on these floats. And then the user also defines the sampling frequency and the spatial float deployment. So in this paper that we published last year, we kind of demonstrated the utility of this new tool with a proof of what we called a proof of concept simulation. It was just a 6-year simulation where we just highlighted what the tool could be used to. We had float sample daily, and we kind of looked a bit more into like float trajectories under sea ice, using these floats to detect changes in deep ocean heat content and ventilation, looking at seasonal amplitudes and ecosystem stressors and how these are sensitive to the sampling frequency, as well as assessing phytoplankton phenology from floats. I invite you to have a look at the paper if you want to read more about these. The test cases that we presented there were really just meant to kind of illustrate what we could use these floats for, but by no means present like comprehensive analyses of each of these topics. So there's a lot more to explore there. Today, I'm not going to talk about these case studies, but want to talk instead about the updates that have been happening since our paper was published last summer. And that's a new synthetic float data set with a Southern Ocean focus that I would argue, and I hope I can convince you, is a better one than the one that we've talked about in the paper. This run has just more years, it has a higher sampling frequency and records a lot more variables than we did for this proof of concept simulation. And after presenting kind of the technical aspects of this simulation or the data set, I want to talk a bit about ongoing work of the project team, already highlighting that all the results I'm going to show today in this part of the talk is highly preliminary, as we've just completed the run a couple weeks at the beginning of the year. So the run that I'm talking about is an E3SM ocean-only simulation on a Southern Ocean regionally refined mesh. So for those not familiar, E3SM's ocean and sea ice models run on unstructured grids called MPAS Ocean, or the ocean models is called MPAS Ocean, the sea ice model is called MPAS Sea Ice. And the model grids, I mean, can really look a bit funny. This is the grid that we're using for the Southern Ocean refined mesh simulation. And here, if you look at the Southern Ocean one, we can see that within the Southern Ocean, here I'm really talking ACC and South, we are at a resolution that can be considered eddy permitting, but we're really not eddy permitting in other parts of the ocean. The ocean biogeochemistry model that we run with the simulation here is Marble in its simplest setup with 3 phytoplankton, 1 zooplankton group. And our simulation is forced by JRA for the period 1958 to 2023. We then deploy floats in the year 1980, and we do this as a function of model resolution. And I'm showing the distribution of the initial positions of each float here in the map. So each dot here is a float that we deploy. In total, there's about 3,500 dots here on the map, with about half of them being in the Southern Ocean region, so in the region where we have higher resolution. So in regions of higher resolution, we just have higher coverage in our model to capture the spatial temporal variability that we simulate there. At the top and on the side, I'm just showing you the longitudinal and latitudinal distribution to just illustrate really the focus of floats in the Southern Ocean. And I'm not showing this here, but just to give you an idea, I mean, this density in the Southern Ocean exceeds the Argo density that we have. So when we talk about synthetic floats in the model, and these are advected with the simulated ocean circulation at 1,000 meters, the same way as real-world floats are when they at parking depth. We of course want to make sure that the velocity field at 1,000 meters is good, or at least as good as it can be, close to real-world velocities. And this is the long-term average of the simulated velocities in E3SM at 1,000 meters. We nicely see really the spatial variability in the velocities, and in particular, the really high velocity bands in kind of parts of the ACC. And when we compare this to an Argo-based product published 2 years ago by Silberman et al., this is plotted on the same color bar. So we nicely see, I'm sorry for the different projections, but I hope it becomes obvious quite easily that if we focus in on the ACC region, our model does a good job reproducing these high velocity bands in places and in, well, both in space and in time and magnitude, as what we see in the Argo-based product. So this is, I think, really good news for kind of moving forward with using the Southern Ocean floats of this simulation. And of course, I just want to start by showing you just a little animation of what this looks like and how densely populated our Southern Ocean is with floats. So here I'm just showing you the first 5 years of the simulated synthetic floats in the model, just in the South Atlantic, a little bit of South Pacific sector of the Southern Ocean. All the little spaghetti lines, when they're black, these are just the 90-day trajectories, and they kind of grade out as soon as they're older. And in the background, you see the surface nitrate field. So we really have a lot of these floats kind of drifting or being advected through the velocity field and then recording really the high spatial temporal variability of a lot of variables they experience. And it's important to say that we advect the floats for the whole duration of the remainder of the run. So we deploy them in 1980. and we kind of track them for the full 44 years of the simulation until 2023. So we don't redeploy. We just ran the initial set of floats all the way through to the end of the simulation. And this is the map you've already seen before. And this is what the distribution looks like at the very end in 2023. If I go back and forth, of course, we move away from the nice homogeneous distribution of floats we had initially. But I think good news is that we are able to keep a large number of the floats in the Southern Ocean, which is why we decided not to redeploy mid simulation. So of course, it's interesting to look at how the distribution changes. And here I'm just showing a different way of showing the map that I've shown you before. It's like the number of synthetic floats deployed in 1980 per 3 by 3 degree box on a scale from 0 to 5. And just to give you an idea of what that density means in the context of BGC Argo float density, I've just pulled all the deployment locations of BGC Argo floats that carried an oxygen sensor. This is just the deployment positions. And just to give you an idea that we have the Southern Ocean really covered with synthetic floats at a lot higher density than the BGC Argo floats that we have out there. That we've had out there since the first BGC Argo oxygen carrying float was deployed. And so just to complete the picture, after 44 years, our densities, I mean, as I've already alluded to, a lot less homogeneous in space, but still, I mean, compared to the real world float coverage, I mean, we still have a lot higher coverage with the synthetic floats, which will be important for any subsampling we'll do from this full float data set as we move on. So the kind of data we get from these synthetic floats, I mean, look very, very similar. I would say identical to the data we get from a real world float. So here I've just pulled a random float and just plotted its trajectory over the full 44 years here on the top, and here just plotting the temperature it records in the top 1,000 meters of the water column over time. And here I'm just plotting one profile every 10 days. And the little dots here on the x-axis give you a bit of an orientation of where the float is. We start at the yellow and then it circles with the Weddell gyre a couple times before it's kind of leaving the Weddell Sea and entering the ACC area, which you can nicely see, and certainly in the subsurface temperature that it records. So this is the kind of data we get for each and every one of the 3,500 floats that we've deployed. And you might wonder what kind of variables we're recording. We're recording a lot in this simulation. This is the full list. I'll leave this up for a moment and hopefully slowly walk through this. There's a number of physical ocean variables that we're recording here highlighted in bold. There's also a lot of atmospheric variables, both BGC and physics, that we record. Again, I mean, with this being in the model world, we can record the atmospheric, like the weather conditions at the time of a sample, the sea ice cover, and all of these things that are, I think, very useful moving forward. And then we have a bunch of biogeochemical variables going on, like from the classical nutrient and carbonic chemistry variables to biology, to rates, biogeochemical rates, oxygen consumption production, to kind of community structure, as well as air-sea fluxes. And importantly, what I want to point out here, we sample with the floats the water column like every 4 hours. And it's important to know that all of these variables that are listed here are available as 4-hourly on the synthetic floats, but they're also available as the full Eulerian classical model output, so the model truth, at least monthly frequency. So in general terms, I mean, the variables here on the left are available at monthly frequency for the Eulerian fields, whereas a lot of these variables on the right here are available as daily fields. So you might wonder, why are we sampling every 4 hours? Isn't that a bit overkill? And I hope I can convince you or show you the reasoning why we decided that this was a good idea. So if we just look again at a random float and just look at its temperature evolution over time, here I'm showing just 10-day, what it would look like for 10-day sampling for this random float. And I think it's obvious that, of course, we recognize, we all are aware that by doing 10-day sampling, we are missing a lot of the sub-10 daily variability that is just highlighted here in this box by zooming in. So 10 daily, I mean, gives us a nice picture of longer term variability, but of course, shorter term variability cannot be captured. So of course, by sampling at higher frequency in the synthetic with the synthetic floats, we can address questions such as what real world floats might be missing when quote unquote only sampling once every 10 days. But an important point to make is that there was also another reason why we made that choice, and that's that all our floats sample synchronously. So it's not like in the real world where one float samples, let's say at 11 a.m. and the next one sample, and then every 10 days, and the next one samples at 1 p.m. and then every 10 days. But no, our floats sample at the same time. So at midnight, 4 a.m., 8 a.m., noon, 4 p.m., 8 p.m. And so by choosing sampling frequency that's higher than daily, we just wanted to ensure that when we construct synthetic data sets from these synthetic floats, that we are able to construct data sets that don't have a bias towards a certain time of the day. So in our proof of concept paper, we had the float sample daily, but they all sampled at the same time each day. So of course, then we do introduce some biases towards the time of sampling on those days. So by having 6 samples a day, or 6 recordings of data a day, we can kind of construct data sets that have a good coverage of all hours, or at least the 6 hours that we sample, but certainly a good day and night spread of the data. So with that being said, I'd like to move to some science that we're currently working on and doing with this data set. And just to highlight again, I mean, like I said, the run was finished a couple weeks or a few months ago, and all of this is very much preliminary. And I first want to talk a little bit about the work that Katie Christensen is doing at CU Boulder. She's a postdoc in the group of Nikki Lewandowski, and she's working on floats in the context of storm activity in the Southern Ocean. Then a bit about what I'm currently working on, which is really quantifying uncertainties in mapped biogeochemical map products from biogeochemical data, including float data. And then the work by Kristen Falcinelli, who's a PhD student at the University of Washington with Alison Gray, who's working on improving methods to map sparse biogeochemical observations. So to start with Katie's project, so Katie is very interested in the energetics of the oceans. So for her, it was an obvious choice to start looking at the eddy kinetic energy as derived from floats as kind of her first project. It's something she's already worked on a bit during her PhD using real-world Argo floats. So now she's kind of applying the same methodologies to the synthetic float data set. And the map here on the left just shows what the synthetic float-derived eddy kinetic energy looks like at about 200 meters depth. And we can nicely see that regions of high velocities that I've showed you earlier in the mean already show up as regions of high eddy kinetic energy in this map of Katie. So for that as well, she's using the 4-hourly float profile velocities that the floats record as well. So it's nice to have this high frequency output for that too. So and then she's now working on tracking storms using existing software called Tempest Extremes, which is basically just identifying sea level pressure minima, and will then work on co-locating the synthetic floats with these storm systems. So what she's showing here is actually the Eulerian eddy kinetic energy around one such storm, so in a 1,000 kilometer radius. And this is just looping over a couple days before to a couple days after the storm. So I'm going to go back to start this over. So you can see just how the eddy kinetic energy evolves over time as the storm approaches. Just watch here for the time. And what she wants to get at in the future is really like, what is the time response of eddy kinetic energy to a storm event? Like, how is eddy kinetic energy affected from the surface to the ocean interior when a storm passes? But also, is this being adequately sampled by real world floats? And I think this is where it's going to be very interesting to look at the synthetic floats. I've just pulled to add to this one map of just one storm example. This is just one storm in, I think, April of 2017 in the South Atlantic or in the Atlantic sector of the Southern Ocean. And the colors show the wind speeds from JRA. And then there's contours shown for the sea level pressure. And what I've added here on top in the big yellow circles are the only two biogeochemical Argo floats that have recorded a profile in the vicinity of this storm on this day. All the small dots on this map show all the synthetic floats that have recorded information at this specific time snapshot. So we really, I think it's very obvious here, and of course there's a bit better coverage for Argo, but we do get, I think it's very clear that we can really nicely start to look at like what our ability or where our limitations are in kind of detecting sub-10 daily, so synoptic scale variability in ocean fields from floats. Yes, I'll leave it at that and move to something that I've recently got very interested in looking at, which is really quantifying uncertainties and mapping biogeochemical data. And I don't have to explain or show this in detail to this audience, but I think you're all very aware that there's a number of excellent products already out there that will be incredibly useful to give us an understanding of long-term changes really in ocean inventories of biogeochemical variables. And all of these studies that have looked at mapping, well, I think I would say most studies that have mapped biogeochemical data to a gridded version have also looked at using models to kind of assess uncertainties in their products or in the sampling coverage, etc. But I think the important point here and the difference to the tool that we've developed is that all of these studies, as far as I know, have approached this problem in an offline manner. So they have a model simulation that was run. They have the Eulerian grid output at a certain predefined time frequency, and then go in and subsample this time average output to kind of compare the mapping method on these data. But the question that I'm very interested in looking at using the tool that we've developed is what is the impact of this offline subsampling on gridded products? So to what extent is this subsampling in time average product adequate to get at uncertainties of data that are in reality like snapshots of the ocean and not like time averages over a large area? So as a first kind of experiment, I'm really just getting into the mapping of all of this. So that's a new thing for me. I've just started by trying or aiming to create the mapped climatological distribution of oxygen. And to do that, as a first step, I've just co-located all the synthetic floats with all the biogeochemical Argo oxygen observations that are available. So here I've been doing this for a 20-year period. I've just mapped out in blue are all the BGC Argo oxygen distributions, so all the locations where we have a profile of oxygen. And then on top of in green, I just plotted the location of the closest synthetic float observation from the model. So this is another or an example of why we decided to over deploy our synthetic floats in space. So deploy a lot more floats than we would realistically ever have in the real world, but also have them sample at a much higher frequency so that when we do this co-location exercises, we really get as closely as possible to the real world distribution of data in both space and time. So here I've co-located the data in lat long space, but also of course depth and then year, month, day, and down to the hour. So I have the same, well, a very similar distribution of coverage throughout a day and throughout a month and throughout the individual years as the BGC Argo oxygen database. To get at the assessment of like the offline versus the online subsampling, I, as a second step, then looked at a regular 1x1 grid, which I define as my target grid. This is what I want to map the observations to. And then I look at each of these grid cells for every month and kind of look at what floats are in which grid cell. And this is kind of then the translation from this map with the blue and green dots to this map here, which just shows like all the 1x1 degree grid cells that are covered over this 20-year period. And this is what I refer to as my online data set. So this is really just the average of the synthetic floats within every 1x1 grid cell for a given month. And the plot that I show here at the bottom just shows you how many synthetic float observations I have in a given 1 by 1 grid cell in a given month. So on the x-axis you have the number of float data points that are used in the average, and then on the y-axis the percent of all data or grid cell points this applies to. And how to read this is that here we have a point at 1, so we have about 65% of all grid cells that only have a single synthetic float observation in them to be representative of a monthly mean. And then you kind of move up as we get to more and more data points. And just the observation I pulled out here is that for about 95% of all the grid cells, so all the 1 by 1 degree grid cells for all the months over the 20-year period, 95% of these grid cells contain 5 or less float observations for a given month. And I guess the question I want to get at is whether this coverage can actually reproduce the true variability in the data set or in the true field of oxygen. I then, after having done this for the synthetic floats to create my online data set, I repeat this exercise using the full Eulerian output. So this classical model truth, the classic standard model output that all the models produce, taking the monthly mean averages and kind of going in and extracting the values at exactly the same grid cells and months as they're covered in the online data set. And I then go ahead and just map both of them with the same mapping tool. And we just in the project using the mapping tool by Kosela and Stein, which is just Gaussian process regression, using a moving window to determine the covariance parameters and to map the anomalies. So this is the result I'm getting when I try to map the online data set. So again, this is the data set I constructed from the synthetic floats. And on the left here is just what the mapped oxygen looks like at near surface, so 5 meters here. And this is on the right here, the difference to the model truth. I was looking at this, I'm like, I'm not sure if this is big or not. And again, as a disclaimer, I'm still working on optimizing the mapping here. And this will be tweaked a bit, so don't take this as like a final result. But I guess what is obvious already is that the mismatch is smaller than 5% in most regions. The mismatch is actually largest here near the coast, but it's actually largest in these regions as there's like very low or no data coverage. So with the parameters I've currently chosen the method unsurprisingly struggles the most where it has the least data to be used as input. But of course, the interesting thing, for me at least, then starts when I compare the offline and the online approach. And this is just what I'm plotting here. I'm just plotting all the covered grid cells in the 2 data sets that I've created. Here on the y-axis, I've called it Lagrangian estimate here. This is the online, so the synthetic float-based estimate. And on the x-axis here, you have the Eulerian estimate, so the classical model output and the way most existing studies would do the subsampling. And the interesting part is here that I'm not showing the histogram here, but the distribution of these mismatches between the two is centered very close to 0. But then there is tails on both ends of the distribution. And I'm just giving you here the 10th and 90th percentile, which are about 3.3 millimole per cubic meter. To be seen, I'm just going to show you what that means in the mapping on the next slide. But before doing that, I just wanted to show you a bit of where these largest mismatches are located. And here I'm just showing you the 20% largest mismatches. So basically the 10% most extreme mismatches on either end of the distribution, one in red, one in blue. And as you can just visually, without having done further digging into this, we can see that the largest mismatches here are in highly dynamic regions, which makes sense. This is where the field might display the largest variability on a sub-monthly scale. So of course it will make a difference whether you have a true monthly mean or snapshots at only a maximum maybe handful of times during that month. So I then went and mapped also this offline data set. And here's just a reminder, this is the map you've already seen before. This is the model truth minus the online sampling. And I'm just going to put up the map now that compares the offline data set to the online one. So what I want to point out here, just looking at these 2 maps and the order of magnitude of the color bar, it seems like, at least on a, and this is again preliminary result, but on a climatological time scale, so for this 20-year period, it seems like the difference between offline and online is rather small overall, at least certainly compared to any mapping uncertainty when comparing to the model truth. But of course, we're not only interested in reconstructing the climatological distribution, but the overall aim, I guess, is to detect trends and change. So we want to be able to reconstruct year-to-year variability in these biogeochemical fields. So I'm still actively working on that. But what I did as a first just metric to try to get at, okay, how do these mismatches that I show here in this map now compare to the magnitude of the interannual variability? I compared the difference between the offline and online subsampling to the interannual variability of oxygen. This is just what I show here. And how I computed that is just looking at the annual mean at each location for each of the 20 years and just looking at the standard deviation of all of these values. Very simple first metric to get at that. And then I basically computed the ratio of the two and expressed it as percent. This is what you get here. It's very patchy. The contour is 20%. But basically, this is really just comparing how large is the mismatch between the offline and the online subsampling, and how large is that relative to the interannual variability of the variable in question. So I would argue that this shows that on a regional scale, so if we now look at certain regions, the difference between offline and online subsampling is substantial when if our goal is to reconstruct interannual variability. So like I said, active research, I'm still diving deeper into this, and future work will kind of involve looking at individual years and the ability to reconstruct trends at different locations, as well as diving deeper into subsurface distributions and looking also at idealized float distributions. I want to very briefly show something that I'm simultaneously thinking about because, yes, I've started with oxygen, but of course there's interest in not only mapping oxygen, but also other variables. I've been very involved in carbon cycle research. I'm of course interested in thinking about mapped PCO2 products as well. And I was wondering whether we can also use the synthetic floats, more generally speaking, as synthetic biogeochemical observations and look at impacts when using ship-based, so SOCAD data in the context of PCO2. So what I show here is a very similar map as the one I've shown you before for BGC, Argo, and oxygen. It's just, I've done the same approach because we've deployed so many synthetic floats. I was thinking, can I not extract the closest float observation to every ship observation in SOCAD? And what I show here in the histogram is just the distance from this collocation in space, so just seeing how far are we off for the SOCAD data. And I would argue we're close enough to do this kind of assessment. So a lot of the data are kind of within 60 kilometers of the true SOCAD observation. So I think we've deployed enough floats that we can also consider using the synthetic observations that we're collecting as not only float observations, but also other technologies. And I've then taken the exact same approach that I've described with oxygen, kind of constructing an offline and an online data set. And just want to very briefly show you something that I produced like last week, is now in histogram form, the mismatch between the offline and the online data sets. And here, I think the key point that stands out is that in contrast to oxygen, the PCO2 mismatches that I get from this analysis between the online and the offline estimates are skewed towards negative values. And at first I was like, oh, maybe there's just not enough grid cells covered in SOCAD. So I just pretended SOCAD and BGC Argo are the same and just wanted to increase the number of grid cells covered and just added the locations of the BGC Argo floats to that to get a bigger sample size. I mean, and the message still holds. I mean, we have the skewed distribution of substantial mismatches in PCO2 between an offline subsample data set and this online constructed one. And of course, this is very intriguing, and I will look further into why that is. I'm thinking about looking at really the diurnal cycle of PCO2 in relation to the data coverage that we have for a given day. I, of course, want to look more closely into impacts on RCCO2 fluxes, again, looking at individual years and our ability to detect trends, as well as looking at daily versus monthly averages that are used in the offline subsampling. Okay, so the last project is very similar in a way, or to what I'm currently working on, but just takes a slightly different turn, I would say. So Kristen's also very interested in kind of just mapping the biogeochemical float observations. She's interested ultimately, of course, in mapping Argo observation or Argo and BGC Argo observations. And again, just gave me this slide, just again motivating that we need the gridded products to effectively utilize the data that we have available to us. And what she's working on is actually using more information than just the information from the variable that you aim to map in the mapping. So what I've shown you and what I've already alluded to before is like mapping uncertainties in my case were largest where we didn't have oxygen observations. But of course, in those locations, we do have other environmental information. We have a lot more Argo data. We have temperature and salinity data that should give us some information about oxygen distributions in those areas where we do not have oxygen available to us. So she's basically further developed this same mapping tool to kind of use temperature and salinity observations in the mapping of biogeochemical properties. Again, she's starting with oxygen, but this can be, it's conceivable that this can be also applied to other variables. So she wants to improve these mapping methods further in the future and will include the comparison with the model truth from E3SM for this development to really kind of pinpoint and pin down the uncertainties that come from mapping, from the mapping method itself versus sampling distributions, etc. And this is basically all I've had today. So I think I've shown you that we've created, I think, a nice synthetic data set, flow data set that can be used in a range of different applications when we're trying to assess uncertainties in any BGC or Argo-based analyses, including the creation of 4D gridded products. And it's important again to point out that our simulation is most suited for focus in the Southern Ocean, simply because that's where the Eulerian, the model grid is eddy permitting, and we can assume that we are better able to actually represent or get closer to the true spatial temporal variability of the model fields, of the fields that we model and try to improve. So I'll leave you with this because, of course, I mean, we've created this massive data set that we only have so and so much time to work on specific aspects. So there's certainly aspects of the data set that you might be interested in and that we haven't even thought of. So just to put it out there, I mean, the data set is about 40 terabyte in size in total. So it's not publicly available as of now. Again, as I said, this is a brand new data set. But if you're interested in using the data in your research now and in the future, I mean, we're certainly open to collaborating and discussing how to already make parts of it available on a case basis. So I'll leave it at that, and I'm happy to take any questions.
All right, awesome. Thank you, Cara. You answered the question I had at the end, which was how big is the data set and how is it distributed?
Yeah, we're still figuring out a way to ultimately, hopefully, make it available in its entirety. But it's again, we're still kind of, I feel like, in a quality control initial exploration phase. So it's still too early for that. But yeah, but that being said, anybody interested should just reach out.
Awesome. Okay, well, yeah, turning it over to the audience for questions, and I see a hand raised from Susan.
Hi, Cara. Thanks for
Hi.
that great talk. One of the things that I would love these data sets to be used for is to actually tell us the time and space scales that are actually constrained by
Yeah.
the array design that we have in hand, right? So, you know, when you look at the core array, I think the time and space scales, and this is without altimetry helping, right? Just on its own is pretty
Yeah.
large scale, right? Multiple thousands of kilometers and probably 3 to 4 months, right? When we go to the thinner BGC array, like what is the actual space and time scale captured by our
Yes.
ideal array, 1,000 floats? You know, is it a 6-month average? Is it a
Yeah.
year? What is it?
Yeah.
In the face of, and I'm talking now just on its own without
Yeah.
the help of altimetry, which, you know,
Yeah. Yeah.
other people have shown altimetry helps a lot. But do you have plans to answer that question?
I would say I think so, because
Okay, great.
it's I got this question a couple times, so it's certainly on the list. And I can say that the mapping method that we're using, I encourage you all to look at the paper, but it does compute the covariance structure from the data alone. So they argue in the, I've not looked at that output yet, but I mean, in a way, there is a covariance field produced with the mapping that is supposed to be only like data driven. So that should already give us some insights there. So I'm certainly planning on exploring that as an output from the mapping method itself. But there's certainly other ways of exploring this. But I just, yeah, it's something that we have on the list as kind of something to look into when we look into tweaking also the mapping and look more closely at what are the parameters that matter.
I mean, you
Yes.
have a very direct way to do that, right? Because you have the true result in your monthly
Yes.
averages. So you should be
Yes.
able to, like, if you
Yeah,
think you
yeah,
have the best mapping
absolutely.
method, you should be able to just do that, correlate, do the
Yeah,
do
just
the
decorrelation,
covariance, yeah, based,
length and
well,
space.
just average and just, yeah, tell us.
Yeah. No, 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 absolutely. Yeah.
Okay, thanks. I'm glad to hear that's in the
Yeah.
pipeline. Looking forward to it.
Yeah.
All right, any additional questions? Come on, I can sit here in silence for a while.
I'll ask another one. So
Sure.
you have a huge data set, right? Which is very frequently
Yeah.
sampled. Could you make a more realistic version of that? That again reproduces, what the one Argo design calls for right now, where you maybe randomize the time of day sampling
Yeah.
and only pull it every 10 days. And I don't know, that could be a smaller data set that more
Yes.
people could use to test the efficacy or not of the current design
That's a good idea.
that we're
No,
trying to implement. Yeah.
it's certainly a good idea. I mean, right now I have it on my list to look at idealized distributions, and I've kind of started that. But I mean, for now, I've kind of looked at, I mean, even just, I think the collocated data set, right? I mean, just
Right.
looking at, okay, this is the data set that is basically the reproducing what we have at the moment. And I think that could already be very useful.
Yeah, but I think as someone who's out there arguing to
Yeah,
get
okay,
the whole
both,
thing
both. Yeah, yeah, I
implemented,
see value in both.
it would be super valuable to be able to say, with this, these are the
Yeah,
space and timescales that we constrain or don't constrain. And
yeah,
that would be really super wonderful.
yeah. Thanks for that input.
Okay, I had a quick one too. If you could sort of go back to talking about the PCO2 exercise real quick and just where that difference between the two sampling method, the result of the PCO2, where exactly does that fit in kind of the, question over how much CO2 the Southern Ocean is taking up and or outgassing?
So I think, so yeah, so I'm not sure yet. I mean, what the answer is to all of this. I think when I started doing this, I was not expecting PCO2 to look so, in a way, so drastically different from just the oxygen assessment. So I'm still working on trying to understand where that difference comes from exactly. But of course, what that means is, in a way, is that we might, and I still have to map out these different data sets to really truly see what the gridded PCO2 difference then is. But what that tells me, of course, is that maybe we're missing something when we map the gridded SOCUT observations, as opposed to, like, we're treating monthly means, or the monthly gridded values provided in SOCUT as monthly means, and maybe we shouldn't be doing that. So there's, I mean, I can't put a magnitude or even a sign on what that means for the flux, right? Because it will highly depend on where and when these mismatches are largest. So it's a bit difficult to say at the moment, but it does tell me that I'm expecting a difference in the flux resulting from the two data sets. And it will be very interesting and very important to understand what the impact is on trends, as opposed to just the overall picture over the 20-year period. So unfortunately, I can't give you the answer yet, but I expect there to be a difference, just given on the large PCU2 differences that I see.
Got it. Yeah, that was an
Yeah.
interesting result.
Yeah, agreed.
All right. Any additional questions?
I have a quick question, more technical, just to know if the size that you gave on the dataset that you have is for the global ocean or just for the southern ocean that you presented?
That's for the global, that's for everything. So of course, there's definitely ways to reduce if we reduce it to the Southern Ocean only. But again, I mean, keep in mind that both for the Eulerians, so the full fields and the floats, we have more floats where the resolution is higher. So even if we restrict to the Southern Ocean, or let's say something south of 30, we will not get rid of the majority of that data. It's not proportionate to the area that's covered, just because we have so many more grid cells and floats in the Southern Ocean just by design. So, but yes, we are able, and that's what we've done with people who already have access to some of the data, that we have reduced it to just the Southern Ocean floats to make it a bit easier to use. But yes.
And what are the criteria of the collocation that you did for the floats and the synthetic floats?
So I just looked at, so for each BGC Argo oxygen observations, I looked at its latitude, longitude, depth, year, month, day, and hour of sampling, and just took basically the closest synthetic observation in space and time for that. So no interpolation, just co-locating with whatever closest profile that we have in the synthetic data set.
Okay, thank you.
Yeah.
Last chance for anyone else?
Yes, I have a question.
Hi.
Yes, hi. Hi, Cara. Thank you very much for the presentation. It's really, really interesting. Yeah, I have two quick questions, actually. The first one is, can you kind of like explain more on the methodological process to create the synthetic observation here? As the first one, and the second one, how is it that related? I guess somehow in my head it's like the same approach, but I just want to hear from you. How is it that related to the observing system simulation experiment? If both are related, how does that get involved into creating subsampling offline and online part?
Yes. So just to, okay, let's see if I understood. Please stop me if you think I haven't understood this correctly. But so just to reiterate, so I think the key point here is that we do our subsampling, what I call online, so during model integration. So the model is running, and at a predefined frequency, we extract snapshots of the properties in the modeled ocean. So which is very similar to the way any observing system out there would record observations, right? So if a ship or a float takes a measurement out there, we don't get like an average over a long period. We get a snapshot at that specific moment. So in a way, we're producing a data set that's very similar to kind of the way real-world instruments look at the ocean. And our synthetic instruments, or in this case, floats, looks at the same way at the modeled ocean. So from my understanding, I mean, in a way that can be considered an Aussie in itself. But of course, what we don't do is kind of any data assimilation or anything. So it's really just a free running model that just extracts its properties online from its simulation. And it's just, yeah, the difference to the offline sampling is really just that when you construct your synthetic data sets offline, so in a way after the model has run, what you often only have available to you is in a way, most often, I guess, monthly means. If you're lucky, you have daily means, but in any case, you will have time averages of your variable of interest. So you then have to ask yourself to what extent your time averages that you are subsampling are representative of the snapshot view that the real world observations give you. So that will, of course, whether that difference matters will depend on your research question and I guess the sampling frequency of your instrument in question. So I'm imagining like a mooring that samples every couple minutes or even every 3 hours will be much more representative of a time average than having a single float every 10 days. To the extreme now. So it will really depend on the question you're asking, but I think our tool offers a way to kind of start quantifying the uncertainties that come from these different approaches.
Yeah. Okay. Interesting. Yeah, just kind of maybe a follow-up. I think with the online approach to create maybe synthetic sampling could help maybe to explore actually the question around the 10-day sampling of the BGC float, maybe by increasing the time resolution to the maybe and see how it's affecting.
Exactly. Even just, exactly. And that's exactly the reason why we sample at such high frequency. So in a way, the user can go in, even just considering like what does increasing the sampling frequency in certain parts of the ocean do, or only at certain times of the year. So you can really start creating all kinds of sub data sets from this massive data set that we've produced, running through all kinds of scenarios. Also, I mean, in our case, you can start thinking about, well, if our floats are dying after a couple of years in this region and we don't have the capacity to redeploy in that region, what does that do to our ability to detect large-scale trends if all of a sudden our float distribution from one year to the next looks so different? So I guess we can come up with a range of scenarios for a range of variables to kind of, get a bit more quantitative, at least, about these uncertainties.
Yeah, thank you. Yeah.
All right. Well, if we have nothing more, I think we'll thank Cara again for the great presentation. And thank you all for joining this webinar. I'll invite you all again, if you haven't yet, to please join our 4D BGC mailing list so you can hear about the next webinar and future activities. So thanks, everyone. Thanks, Cara.
Thank you. Bye.
Bye. Thank you.